Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
With engineering research and programs, and on behalf of Jim Laris, it's a pleasure for me today to have this talk by Larry Leifer, professor of mechanical engineering design from Stanford. And so he's also going to be joined by Jan Chong, fifth year doctoral student from the Department of Management Science and Engineering at Stanford University. Over the past year, we have been contributing to some of the research efforts for Larry's work at Stanford. So, without ado, I'd like to present Larry.
Okay.
Thank you.
Thank you very much, John. Partly for the audience's information, I'm a very hard of hearing guy. When we get the Q&A, you wave your hand and I come out with my own microphone and interview you. With the podium this far from the screen, I'm going to tend to walk around. I'm delighted to be with you, and I'm going to try to do a little bit to entertain. The first thing we'll try to do is to give you a little bit of our background. Where do we come from? Why are we interested in the way people design, build, and operate systems, complex systems? Historically more in the world of aerospace and automotive industry and consumer electronics than in the software itself, but increasingly the software because it's now the biggest part of the product. And then Jan will present preliminary results from a study of pair programming activity in which we're specifically trying to get at the what are they doing and why. And the hidden agenda is if that's what they're doing and we understand why, then how can we help them do it better? And the third component of the presentation is to share with you what's hot in the Stanford community on getting at issues in design and what I understand from the morning's conversations you might prefer to call software architecture versus software design. I think we're talking about pretty much the same issue, but we have some different language for it, and often that's the beginning of confusion in product development. So, where do we come from and why? The primary mission that I have as a design engineering educator is to redesign the future. And this image is a little bit of a biographical sketch on where I think the future is headed. I'm going to act it out just a little bit. When I went to college as an undergraduate, I was kind of that guy, right? Hairy, right off the beach of Southern California, and then I had a bachelor's degree and then a master's degree. Actually, I better tell you what, this was general engineering science, like no major. Art and engineering, what's that? Neurosciences, ooh, that's big. This guy's got a PhD, he's gonna be in charge of the world, he's got tools, he's got knowledge, and then he gets an assistant professorship and an associate professorship and a full professor. The whole life is a keyboard. And what I want to convey a little bit is the sense that my students come in looking like that. And I'm really anxious about their engagement in the world, the quality of life, the ability to know and understand at a large level, a broad level of human values and potential versus just things that come through keyboards, things that go through displays of whatever scale. And we know what the next step is because we're already there. That's the next step. Now the keyboard is that scale, right? So, in fact, I think this is really a very, very timely, acute concern for all of us. If we don't get out there and start redesigning the way things are, that's where they're going to go. And they've already got a 5 to 15-year lead on us. So if we don't start, we're in deep trouble. And of course, changing the universe isn't easy, so we should start sooner and with more vigor, and you guys are part of that change the universe scenario. Well, we spent a lot of time looking at the future in our new product development group. So I share a little slide of a group. You recognize the icon for Audi. Would you believe that Audi's vision of its own future is this car, as was made for the movie I, Robot? How many have seen I, Robot? That's good. You're folks like me. I go to movies like that. Okay. In the movie, you might think that that android thing in the background is the robot. Well, and maybe it was. But the robot that really got my attention is this guy. Because this guy's going to be in my lifetime. This guy is already on the road, parts of him. And he's going to have autonomy, and he's going to have intelligence, and he's going to have sensors, and he's got an operating system that never reboots. Or it does so quietly and doesn't tell you, right? Okay, so we're very concerned with the future and how we should go about getting there. One of the ways we get at the future is to have companies bring projects into the university environment where we can study how product development could be made better. So you get a little sampling of what the projects look like. This year, there's a strong automotive industry representation because automotive industry is desperate to innovate. And you'll notice from the labels that they're mostly trying to innovate in the cockpit with electronics, with smarts, with sensors, with software. The most dramatic example is perhaps Audi itself. Again, they want us to prototype the co-pilot for the year 2020. And the team is in the process of building that right now. And they've come to a really wonderful insight. They've discovered that in 2020, we don't need a co-pilot. Because the car's got all the maps in the world, it's got GPS, it's got totally drive-by-wire, computes its way down the lane and doesn't go out. You and I can take a break. What do we do with our break? We start doing the internet, we start doing SMS, we're doing watching a movie, we're talking to our friends, we're totally involved in communication tasks. And therefore, it becomes the co-communicator of the future. And the team's trying to build a system that actually makes sense for that role. The other feature of our community is that we're very engaged in delivering teams, not always unit teams, but people who are completely prepared to be on teams, to launch new companies, to invent new haptic interfaces to the world, to produce water fountains that are the greatest experience we've ever had. And maybe our best known spin-off is a company named IDEO Product Development, now one of the leading companies of its kind, and a full 7 times larger than its nearest neighbor. So they've become a real kind of flagpole for where things could go or should go. Maybe even sometimes shouldn't go. Let me try with this image to represent what our research group does that's a little different than most technical development groups. In a typical scenario, let's invent the BMW of the future. We would get a group of product requirements, we'd give them to the product development team, and they would produce technical outcomes, specifications, performance data, whatever, and we would feed that back in a technical loop to monitor performance. Are we meeting goals and requirements? What we would not have is instrumentation on the human element in the product team. So the stress and the emphasis for you to see is, sure, we do the technical loop. We have to. What's novel is to instrument the product development team itself so that it is better able to perform its job. It's not that we'll controlling them. We're giving them information about their own performance so that they can make intelligent choices and decisions. So let me show one example of the kind of project that happens in this environment. We were working with VW last year, and they wanted to explore the notion that the driver should be able to say, close the window, or turn up the radio, or keep that person out of the car. Gestural interface to the vehicle. Very early in the project, actually within about the first 5 weeks of the project, out of a 30-week project, we're in the car, we're starting to take over the cockpit, we're putting displays and sensors in place so that we can begin to explore how would this actually work in a car, not just thinking about it, but being in the real world of the customer. And the group came up with the notion of controlling the common center control panel. How do we handle the AC? How do we handle Windows, entertainment? And this was the zone in which they implemented a machine vision system. And I chose this example because machine vision is your business. It's software engineering, it's algorithms, it's making sense of noisy data, trying to extract the signal from the noise, trying to make sense. The same software that's used there was in part used in Stanley, the Grand Challenge winner. So it's not like it's low-end stuff. It's right off the top of the CS department. And you put it in the cockpit, and it's really hard to get reliable performance. The team continued to develop this and refine it, and by the end of the year, yep, we could operate all those systems, but we weren't very happy. Audi was very happy that we did it for them, and they didn't have to. The second of two examples I'd like to share with you comes out of the world of software engineering, electronic arts. One of my doctoral students was employed full-time there, had been there 5 years, and he'd been collecting data. I'll let you read that essentially, from multiple cycles of product development. He had access to all of the code, not in the sense of when it was checked out, checked in, bug reporting, and knowing who was working with the code at any given time. There's a very intense development cycles, very real-world industry scenario, which I'll footnote is very hard for us to get this kind of data in the real world. It's extremely hard to get inside a company. People concerns, privacy concerns, intellectual property concerns. The fact that he got it is fantastic. So what? So let me try to walk you through his slide. It's not easy for me. Lines of edited code. Timeline. Milestones. First release, re-release. The blue line is maybe the background is the amount of code checked in and out. You see it's very high level of fluctuation. The average ramps up over about a month, and it's pretty steady state, and it goes right on at that steady state. That gets a push. You read that, I'll let you do that yourself. Okay. This is one of the ones we especially attend to, and that you guys probably feel special pain with, the feature creep scenario. A different view is to look at lines edited and the moving average of how much of the code was being edited solo versus concurrent, more than one person working on that module or unit at any one time. So one of the things we learned about group programming was that in these initial, typically highly formative phases of a project, but not the main production phase, but they're deciding what will be built and why. And then when we go down into production, we get this incredible ramp up to absolute frenzy and madness and burnout they're gone. And then they take about a 2-month break before they even come back to work. Data, lots of data. He's still mining it. It begins to give us some insights into the dynamics of software engineering. There's often a tendency to see work as steady-state processes. This cries out how dynamic it can be. Okay, that's what we do. And now a glimpse of what the design thinking research has yielded over the past 15 years or so. We study people at work and we try to figure out what's blocking them and what would help them. Our core methodology is simply to observe. This represents video interaction analysis. Look at a team doing their job, record the video, microanalyze the video. When Jan presents her work in a few moments, that's a similar scenario, though she wasn't using video. The next example comes from a field work we did at Ford Motor Company. I didn't say that out loud, did I? We were invited to come and look at what happened when they introduced a new product development methodology into the company. The whole story behind that, but the new, everybody does product development the same way now, folks, and they give that to a group of experts. The experts go to the product development teams. Product development means try to turn out the real car, and we try to track where the knowledge is. There's knowledge in a loop here, people working together, lots and lots of tacit knowledge. There's the formal reports and documents that go back into the corporation and management. And the thing that got our attention was there's a loop here coming through this consultant, process consultant. And as a result of this, we've formulated several lines of research that look at this role. And the big issue in this domain is the decisions that are made go up there. The reasons for those decisions are hidden. Only the coach can see inside and report outside. So the key to capturing tacit knowledge, the rationale for things, may be actually in the hands of a real person. Okay, one of the big findings, this was actually software development challenge at Xerox PARC, human-computer interaction, and John Tong was wondering how is information managed? How is communication managed? So the big point was that you store text. Yep, no surprise. You express ideas with sketches. Not such a big surprise either. You mediate interaction with gestures. How many of you have a computer that records gestures? Excellent, cool. Sketch, notepad, okay, right on. Well, remember, gesture was what we were trying to do in the car, too. Gesture has long been a missing signal with a huge relevance to workflow. Negotiation during group work is a huge effect. The next piece I want to share with you was by Vinod Bhaya. He's studying a situation where people are in a product platform situation. The last generation product or vehicle subsystem now has to meet new requirements, and he's studying how they use information. He's looking at several versions of the information, how they produce it, how they retrieve it, how they search for it. But the most compelling finding of all was that no matter how they were dealing with information, they had an attention span with a median of 6 seconds. I suspect that describes a lot of software engineers. If it doesn't work like that, I'm out of here. I'm on to the next bug. Things like that are very common in our world, and the better you are, the shorter your attention. So the experts move this to the left, and the novices move it to the right. So our environments for supporting design have to be very responsive. This one's a little more abstract, but it's really interesting. We have a situation in the course where the design teams, I should mention the design teams are typically 3 to 4 people. They produce a final report after 5 weeks, after 15 weeks, and after 25 weeks. That's the full documentation of the product and the process. Adi Mabagunji was looking for the questions they asked, and it was difficult to find, so he ended up counting noun phrases. Quick definition of a noun phrase. It's the screen height, the screen width, the surface texture, the line width, the font shape, anything that's descriptive. And he found a distribution here. He found that all teams added more unique noun phrases as they worked and continued to. And after living with this graph for almost 2 years, we finally saw the blue and the red lines. Some groups start off at a lower level, and they don't learn as much. They don't add new language. And some start higher and learn faster. And these are the high-performance teams that win the prizes, get their product on the market. These guys aren't bad, but they're the mediocre outcomes. This was a huge discovery that the language people use while they're working is an important metric of the progress being made in a project. And the last one I want to share with you was from Iris's work, where he nailed the question issue. He did it by using video interaction analysis, incredibly time-consuming. But what he found was the performance of the team was a function of the number of questions asked per unit time. 40 questions an hour. That's a lot of questions. What kind of questions? Deep reasoning questions, that's analytic thinking. Given some alternatives, how do we choose amongst them to produce decisions? And generative design questions, the questions we ask to expand the design space, figure out what the options are and the alternatives. And the two go together. You've got to diverge, then you got to converge. And you do that 40 times an hour. This is an incredible process. And what we know indirectly is that the decisions get recorded and the questions don't. So very often when we try to get back at the rationale behind what happened, we don't know the decision in response to what question. Big deal. Hey, we're at part 2. Let me introduce and hand control to Jen Chong, who is. Maybe you should describe briefly how you see your role.
Okay. Okay, hi, my name is Jan Chong, and I'm a PhD candidate in management science and engineering, and I'm a research assistant on one of the studies that are part of many studies that are going on in CDR right now. So we thought we could use a more expanded view of what one of the projects in CDR is like. And so this is on paper. So to give you a little bit of background about the whole project, this is an interdisciplinary project. Flies across from both computer science, Department of Mechanical Engineering, which is where the CDR is located, and then I'm in management science and engineering. So that's kind of a big picture of our research team. And to give you some idea of the project motivation, this came about when one of the members on our research team found out about pair programming and started getting interested in the pair programming phenomenon. So there are a handful of studies out there that have been done to compare pair programming performance to solo programming performance. And in general, these suggest that pairs write better code, usually by things such as defect rate, time to completion, also team morale, in less time. Pairs do better than solos. But there are two, so this makes it pretty compelling sort of practice that we wanted to take a closer look at. But there are two sort of main limitations to these studies that are out there. The first one is that these studies primarily look at outcome measures. So they're not looking at what people are doing when they're actually in pairs. They're actually just measuring what happened. They're taking measures of the code that was produced. right, or issuing surveys to the programmers after they finish their code and comparing those numbers that they measure. So what you were
This one's definitely working.
Okay, are we good? All right. So where was I? Oh, looking inside the back box to actually see what it is about to people and what's happening, what process is going on that leads to these better results that these studies have documented. The second limitation is that the majority of these studies have been run on student programmers because they're academic studies and because that's what's available to them, and not on professional programmers. So that really raises the question of how much do these findings translate to professional programmers working in a completely different environment than what students do in the classroom. Okay, so when we started this project, this is a diagram Larry came up with that kind of says what's the difference between a pair and a solo programmer. And so the solo programmer is kind of at the top, like about what does he or she get in, product requirements and software specifications, and then what's the process that goes on when they develop software, right? They interact with the development environment and the software code and what's going on there. And we kind of hypothesized that in this sense there were two roles now. We had the driver and the navigator, and there's all these new feedback channels and interaction channels that are going on between the two programmers. And so that's kind of our starting point for thinking about what's going on in these processes. So the way we designed our project to explore this is based on a lot of the other research done at CDR. It's a two-phase project. It starts with ethnographic observations in the field, followed by a lab experiment that then is informed by what we found in the field. So I'm going to talk about each of those phases in greater detail, and in particular I'm going to really focus on the ethnographic phase because that's what we've completed and have been busy analyzing the data to date. We're about to start the lab phase, and that's something we wanted to get some feedback from people here on, is what they thought we should do with this in particular. So phase one, the actual ethnographic observations occurred from April to August of last year, and what we did was we found people in the workplace that were actually pair programming as a part of work, and we watched them work. And I'll talk a little bit about what we found about that. And then from September to pretty much now, what we've been doing is going over that data repeatedly, trying to identify what we see as interesting and what we see as our hypotheses for what's going on in there. Okay, so how many people here are familiar with ethnography? Okay, so not bad, but not everyone by far. So I thought I'd give a bit of an overview what that is. It's a methodology that comes to us from the field of cultural anthropology. And the main idea there is to strive to understand the world from the perspective of the people you're observing. And you do this through intensive observation of what they're doing, their actions, the artifacts they interact with, and their dialogue in the context in which all these interactions occur. And so in practice, what that means is we sit behind people, we take video if it's possible, although that's often not possible, especially in an environment like a professional software development company. And then we go through all that data to try to find patterns. So in this case, we conducted ethnographic observations at two sites. These were mid-sized startup companies in Silicon Valley, two teams, one in each company. And in this case, pair programming was used as a part of extreme programming. We did try to find pair programmers that were not in the context of extreme programming, but that proved difficult to locate. So both of our sites ended up being pair programming in the context of XP. And if people are interested in that, I can talk a little bit about the more XP side of things too. Okay, so our two teams, which are pictured here, Team A on the right and Team B on the left. Team A was formed in January of 2004. The start of our observation period, which is between 3 to 4 months. I believe for Team A it was 4 months. It had 6 developers. They had hired 3 more by the end of the observation period, 1 full-time developer and 2 consultants. On this team, pretty much all the work was done in pairs. Every morning they would meet, have a status meeting to talk about what they'd done the day before, form an ad hoc pair, and then they'd sit down to get work done. Team B was a little bit older. It had been formed in early 2002, so it's a little bit bigger, had 9 developers. They hired 1 new developer by the end of the observation period. All the programming work on this team was done in pairs, but they had specific days set aside for practices such as spiking, exploratory programming to look for different solutions, and testing, which they did by themselves, so individually. Okay, so what do I mean when I say we did ethnographic observations? Well, we visited each of these teams weekly. Across a combined total of 5 months for both teams. We spent about 3 months at least with each team. Each time we visited, we spent between 1.5 to 3 hours with that team. It actually ended up being a bit longer than 3 hours for Team A. We'd often also go to lunch with them or hang out with them a little bit afterwards, so that added to the time. When we were there, we would usually sit behind a particular pair of programmers and basically just try to absorb everything they were doing for that day, taking notes often as rapidly as possible in order to capture as much detail as possible, noting both their actions, their dialogues, and the context for the action and dialogue. We use audio recording in order to better capture the dialogue that was being spoken in the course of programming, which we then would go home and transcribe, and then integrate those transcriptions with our notes in order to get a very detailed transcript of every single session. And so to give you an idea, these are about 40 to 60 pages per session. After that, we would go back and review them, reread them, and then something we call coding, which is not really what most people think of as coding, which is the systematic identification and then categorizations of behaviors. So the idea here is that if we go through the data and find something that we think is interesting, we want to make sure that's not idiosyncratic to a particular person or a particular session. So we go through all of the transcripts, look for that behavior, and make sure that it's a persistent pattern. Okay, so some provisional findings. So what we came up with is kind of this collection of, I think, 4 or 5, we called them findings because they were really documented by behavior in the field, and then 3 more that were more hypotheses that's kind of informed by what we saw going on in the field, about what we think is interesting about pair programming, and in some cases what makes pair programming really work. So our first one here, one thing that was immediately obvious when we talked to programmers, the literature on pair programming, and in fact the developers themselves, when asked to describe how pair programming worked, would tell us that, well, there are 2 roles that pair programmers break up into. One person is the driver. They control the keyboard. They kind of think about things at a lower level of abstraction. They're really concerned with immediate implementation issues, figuring out what code goes next, what's the next line of code. And the other person's the navigator, and they kind of operate at a higher level. They sit back. They offer feedback. Think more strategically is a phrase that was frequently used to talk about how these roles worked on a programming pair. So in some sense, it's the gray lines on this diagram would be what people constantly told us that they were doing, even the developers that engaged day to day on pair programming. Now what we found when we were observing them is that this isn't what they were doing at all. In fact, what they did was there was no real separation in the level of detail with which they approached the problem that they were working on. In fact, they were really tightly coupled. They would both have a conversation at a very low level of detail, and then at some point one person would maybe say, like, wait a minute, is this really the issue that we should be thinking about? What if we conceptualize this test as a X, right? And then they would both kind of start being like, okay, well, if we think about that, it'll interact with this module in this way, and we can start reconceptualizing it, and then they'd be like, let's try it out. Let's take a look. And so they were kind of moving through this problem space, going between these levels of abstraction, but in a way that was very tightly coupled together. So not the sustained level of abstraction. Yes?
You mentioned the word test. So these guys are doing test-driven development as well?
Yes, they were doing test-driven development as well.
Is there an observation about one person thinking about the test and the other person implementing the test?
They didn't really, like I said, they kind of both worked on it at the same time and thought about it at the same time. So there isn't really this sense of one person's like, oh, I'm going to write it, and the other person's like, wait, this is how it should go. Except, I'll make that exception. This wasn't always the case. When there was a huge knowledge disparity between the pair, then we did see something that was more like one person is really driving the interaction, the other person's thinking about it on a different level and giving more distant feedback almost. But the thing about that is this would occur regardless of who had keyboard input, right? So you could have the navigator really being like, okay, what we need to, the next line of code, to the level where they would be like 4i equals to the other person. So is that kind of, okay. Okay, so that was really interesting to us because, again, it goes against everything that's been kind of written about pair programmers and, in fact, what the programmers themselves thought they were doing. So, again, to hear, it says our initial conception was also incorrect. So we had, something else is going on here. The second finding, again, that we totally didn't expect, we didn't go into the study looking for this, but what we did find was that programmers are constantly interrupted in the course of programming, which those of you who are programmers are probably like, duh, but it takes researchers a little bit while to figure out what's going on. And what was interesting about this, and this draws on data from a separate ethnographic study of solo programmers that is also done in the same organization as Team A, so they're within the same company, but two separate teams, one which uses pair programming, one which does not, is that the interruptions are consistently shorter for the pair programmers than they are for the solo programmers. And so I kind of give you some numbers here, which is the total observation times that we have that are analyzable from each team, the average duration of the observed interruptions across the team. The number in parentheses is the number of interruptions for each condition. And then what we did was to try to get a picture of what's going on, we broke them down and we coded each of these interruptions by both source, they're self-initiated interruptions or externally initiated interruptions. So if you stop work yourself to do something else, or if someone comes into your cubicle to ask you a question, forcing you to turn away from your work and address them, or what type, an intrusion, a distraction, or a break. And across all of these categories, the pair programmers are always shorter average than the solo programmers, and sometimes by quite a lot. Yes?
Shorter average, but more of them.
Uh-huh, but more of them, yes.
Why did they have, why did the intrusion one seems odd to me, because in that case I would say solo programmers are better off. They don't get as many intrusions.
And so?
I don't know, I'm just, seems like more.
Well, one thing you have to remember is these pair programmers are radically co-located. Because again, this is part of the XP team, so that adds a little bit of noise in here. But nevertheless, which I think explains why they're more interrupted. They're in the same space. It's easier to interrupt someone. You go over, and it's more distracting as well. But even in that space, right, they keep their interruptions much shorter. In some sense, you would think they would be maybe more distracted in that sort of environment. But no matter what happens, the solo programmers kind of.
I misinterpreted because I thought I heard you say. I applied the cubes to this, so that's what was in my mind.
Okay.
When you study solo programmers, who did you study?
What do you mean, who?
The test writers at Company B?
No, they had two product groups. One of them used XP and pair programming, and the other one did not. The other one used a modified waterfall process. People worked in individual cubicles. They had,
I guess the other thing, too, every time you're interrupted, there's a context switch.
Mm-hmm.
Probably doesn't get factored into those overall numbers either.
Mm-hmm.
So probably those numbers are greater than they show.
Yes, that the disparity between the two teams is actually, yes. So we could talk all day about this one. In fact, I'm more than happy to do that, but that's not what the talk's supposed to be on. So, but feel free to ask me questions about it later. So there's a whole host of reasons why we think that's true, but kind of the broader reason we have is the pair programs are more mindful of workflow and then also tend to bring each other back to task is kind of the general summary on that. We also looked at pairs when they were talking, and we noticed one thing is that the pairs have an overlapping but usually non-identical pools of programming knowledge, skills, and experience, right? So if you think about, one programmer has one of these circles, but two programmers has this whole Venn diagram, and some other knowledge is going to overlap. And that means that they have easy, ready access to a much larger knowledge database, which probably allows them to produce higher quality code more rapidly. They have access to different design patterns more immediately. Knowledge about particular parts of the code is just bigger for the two of them. One question that this raises is that what's kind of the right combination for two programmers that are pairing, right? If you kind of already buy the pair programmer thing, like, do you want people that have a lot of overlap or very little overlap? This would seem to suggest that little overlap is good, but we know from studies of interactions that you need some sort of overlap in order to be able to communicate, in order to be able to function as a pair. And so that's one of the things we don't know, right? What makes for ideal pairing. The second one is that the pairs would come in, even if they heard the problem the same way, from the same people, or read the same docs, they still come away with inherently different conceptions of the problem. So, programmer 1 thinks it's this concave thing, and programmer 2 thinks it's this kind of convex thing. And before they can work, these pairs tacitly would require agreement on what the course of action should be before programming. And in the course of getting to that agreement, they had to negotiate the problem boundaries and the potential solutions. And that resulted in a very thorough search of the solution space, much more thorough than what we saw solo programmers doing. Again, there wasn't supposed to be solo programmers in the study, but I watched a lot of them, so. Okay. Pair programmers had the ability, which solo programmers do not, to engage in continuous review of the design and the code as it emerges. This is that immediate feedback that you get from simply having a second pair of eyes. And we did see them catching a lot of code defects early in the programming process, ranging from very simple things like you're missing a semicolon on that line, or their function name is spelled wrong, to larger things like, wait a minute, how does this work in the context of that module? Was this going to break the module or the interaction we already have programmed in there? And then moving on to hypotheses. Now these are 3 things that we think are going on, but we're kind of less able to prove because of the data we had and the form it comes in. One thing we thought relevant to interruption is that pair programmers seem to be able, well, first of all, they were able to continue making task progress even when one programmer was interrupted by just inherent nature of having a pair. If one person gets pulled away, the other person continue making progress on the task. But 2 things we thought might be going on is, one is that they recover more rapidly from being interrupted because they were able to serve as an interactive means for you to return to the task. So you think of it as a solo programmer trying to pick up where I was in terms of working. All I have is my state, whatever context I kind of remember, what the physical artifacts around me indicate when I come back to the computer. Well, if I have a partner, I can just ask him or her and be like, what were we doing? What's going on? And usually they do it unprompted. You sit back down and your pair will say, oh, what I'm looking at is this line here and I'm trying to figure out X. And so that might ease how rapidly you get back into the problem. The other thing we thought is that they were socially motivated to address interruptions more rapidly than solo workers. You have someone waiting for you back at your computer. You're supposed to be working as a pair, right? So you're going to kind of speed things up in order to get back to the person that you're supposed to be working with. So, corollary to this, as a result, pairs may incur less workflow degradation over time due to interrupts, and while maintaining the high levels of attention focus that they need to produce top quality code. So interruptions may be less disruptive to pairs than they are with solo programmers. Hypothesis 2 has to do with kind of cognitive load, something again drawn from both watching the programmers and a little bit of experience ourselves when we tried to work in pairs, is that pair programmers have an opportunity to share a cognitive load of pair programming. That means that when you're sitting there, if you have a solo programmer, they'd be making a lot of effort, a high cognitive effort into their work task, but over time as they grow tired, they can't sustain that effort. So by necessity, it kind of like degrades, and maybe you take a break here, and so therefore you're kind of starting to come back up here if you're working on a particularly difficult or taxing problem, for instance. Well, because there are 2 people in a pair, what you can kind of do is switch off, right? You can take breaks while your partner is still kind of operating at a high level. What this means is that the pair as a unit potentially sustains a much higher level of cognitive effort across the entire period of time. Yes?
What this suggests is that 2 solo programmers achieve a higher total mental effort than a single pair of programmers, if I'm just adding 2 solo graphs together.
Like if you just aggregate 2?
Yeah.
One on top of each other? Yeah, so keep in mind this graph isn't, I just drew it in PowerPoint. So conceivably the crash downward is lower. I don't have exact numbers for that. But
it seems like an interesting thing to study, whether pairs are more effective than 2 people rather than just one.
Yeah, and that's, the reason this is a hypothesis is because we don't have data, at least in the ethnographic form, that allows us to make that assessment. But yes, I agree. That's a very interesting perspective. Okay, and the last one draws a bit on social psychology. Is the idea that pair programmers are facing the prospect of constant evaluation by a knowledgeable partner, which in a lot of social psychology studies have proved to either facilitate or impede your performance on a task, depending on how well learned or unwell learned that is. And so one thing that we suspected was happening on here was that, spurred by the expectation of being evaluated, individual programmers in the pair are working to a higher standard of social commitment. So they force themselves to write better code. They have more elegant designs. They don't settle for like the hacky solution because they know someone's going to be looking at it and being like, what is that? Yeah.
Well, these guys were also being videotaped and recorded. And do you think that changed their behavior?
So in this sense, in the ethnography, they were not being videotaped. They were being audio recorded, and I didn't tell them I had a CS degree. So actually, they thought they would like over-explain Dole to me and stuff like that. So that idea was that I was trying to reduce how much evaluation apprehension I would.
Not that being evaluated by another CS PhD candidate, but just that there was somebody there, but they were on the best behavior.
Well, I watched them over 3 months for over 40 hours. So, I mean, in some sense, probably the first time, but over time you tend to drop that. One thing I did notice, again, from my other study of solo programmers, is that the first time I was with a solo programmer, they never goofed off for the entire 5-hour period that I was sitting behind them. But the second or third time, people were watching Star Trek videos while I was sitting there running a tape recorder, so surfing the web, so reading Wikipedia. So I think after, they can't sustain that, basically. Okay, so, all right, to get back. What we're in the process of doing now is trying to take all this information and pare it down into something that we can then translate into a lab study. So I'll talk a little bit about what challenges that are facing us and what we hope to get out of a lab study. So what can a laboratory experiment tell us that an ethnographic study cannot? And I've kind of touched on this as I talk through the hypotheses. One thing is isolation and control. The factors are inherently confounded in the workplace, right? The lab environment potentially allows us to really isolate and look at a particular factor, or at least control for certain factors across the different pairs that we're studying. It allows independent replication. I mean, for all we know that maybe these two teams are actually just completely weird, right? Does this behavior, does this same dynamic occur across multiple programmers coming from different backgrounds? Is this something that's inherent to pair programming themselves, or is it something that's a function of XP, or the team setup in those particular developed environments? One thing that's not on the slide that the lab also gives us is performance measures. I couldn't get them to let me look at the code, so I have no performance ratings for the pairs that I was observing. And so the lab would let us take the code that they write and actually be like, who has lower defect rates, who completed things faster, who wrote better code. So then what we're facing is, how will we translate these observations and speculations, hypotheses, into a series of experiments that's appropriate for the laboratory environment and relevant to management and developers. So we have two kind of challenges facing us. One of them is recruitment. We want to run the study on professional programmers, but they are difficult to recruit, and as you all know, their time is very expensive. And then the challenge of face validity. There's an inherent tension being able to isolate a particular factor for study in the lab with how closely whatever task we have them do is going to resemble a real work task or a real work environment. So those are two challenges. So I'm going to talk a little about the resources we have available to us. The first one is the Stanford CDR Design Observatory, which is a great lab. The video analysis that Larry referred to kind of gave fruit to this. It's a lab that allows us to put developers inside kind of a fishbowl room. We have 4 cameras running at them to capture different angles. So here you see, there aren't computers in that one, but in this case, this is our pair programming setup. So we have one to look at the screens. We have what they're actually facing, so you can see expression, a different angle on the screen, and an overhead view to capture, although that's actually a little bit off. We meant to slide it that way to see what they were writing and drawing as they were coding. And so that gives us kind of, we also have continuous screen capture as they're working, and audio capture of what they're saying as they work. So this gives us a really much more complete picture than we got in the workplace of what's actually going on, and allows for a lot more microanalysis of behaviors. For instance, interruption recovery, right? We can now time based on their gesture and where their gaze is looking at it when they turn their attention back to the computer, which has not come through in the written and the audio data. The other thing we did was we developed a video analysis tool in order to handle all this stuff. It's called VACA, and it handles all these streams of information, allows you to identify and categorize behaviors, much as we did with the written transcripts, only with video and audio synchronized this time. And I don't have a lot of detail on that, but it is available on the net. So if you go on SourceForge, you can see the source code and talk to the the other RA on the project who's working on this. Okay, so based on these, we kind of came up with a bunch of experiment ideas, and then we pared them down to kind of the 3 most feasible ones, which are the ones I'm going to talk briefly about right now. And each of them answers a different question. So one of the things we really struggled with on this project is pair programming is a pretty nascent phenomenon. There hasn't been a lot of in-depth research on it. So what do we really want to try and say with this one opportunity we have to create a lab study? And so I'll talk about each of the 3. The first one, our guiding question, was a very basic one. Can we replicate workplace behavior in the design observatory? So is this stuff going on in a way that is inherent to 2 people on any programming task when you tell them to pair, or is there other stuff that's going on? So the idea here would be to bring programmers into the lab, complete a work realistic task of maybe 3 or 4 hours, and then vary some aspect of the configuration or the task maybe, sort of like poking ants with a stick to see what happens, right? Like give us a different picture, controlled ethnography, if you will, of what's going on in that lab. And the basic idea here would be verify that the mechanisms occurred through ethnographic observations still occur in the lab. We get to measure the effect of a controlled intervention on these behaviors, and then correlate this behavior measure to pair performance. So again, more verification rather than truly new, right? See what if we found in the field translates to the lab. Experiment B, we took looking at the interruption behavior. Again, a real surprise to us. We didn't expect to see this in there. But do pairs really recover more rapidly and more effectively from interruptions than solos? As I mentioned before, we really didn't have that great of a picture of what they were doing pre and post interruption in the ethnography, not down to like gesture and gaze and posture. The lab gives us an opportunity to do that, to really be able to say, like, cognitively, where do we think changes are going on. So we can bring pair and solo programmers in to complete a work-related task, interrupt them periodically as they work, control the nature and the timing of the interruptions. We didn't have any control of that in the workplace environment, obviously. And then try to better understand that impact on programming performance. So this gives us a better picture of that particular phenomenon in the programming data. So this is pretty interesting because there hasn't been a lot of studies on interruptions on pairs in particular, or on pair programmers. But it doesn't really address the question we kind of set out to talk about, right, which was the where and why of pair programming in general. And it definitely doesn't explain pair programming improvements in non-interruptive environments. So interruptions are never mentioned in the previous studies, although they're done on students in the classroom, so presumably they're getting interrupted as they work as well, but that's never been captured. Okay. And the last one that we had, again, these are kind of random cuts. We did a lot of brainstorming. I had to filter down for this talk. So the last one, it was how much of this pair programming effect comes from social facilitation? Can we bring 2 programmers in to write and evaluate small pieces of code alone and in pairs? Compare the quality and evaluation ratings across different conditions as well as across different levels of expertise. If I pair you with a first-year student, if I pair you with someone I tell you has 10 years of experience, that's considered an expert in the field, does that change how you code? And try to sort of isolate that compared to the effects of knowledge pooling, problem negotiation. So 2 issues with that one that we saw is that the effect might not quite be strong enough. It might be very subtle. So we might need a big sample in order to induce that effect. And the second one is that when we start talking about writing and evaluate small pieces of code, we're getting at a very narrow slice of that phenomenon. We're not really capturing the heart of everything in pair programming. It's just taking one small slice. And maybe at this early stage, we want to go for a bigger piece instead of trying to hone in so much on one small one. And I think that's it. Mm-hmm, yeah.
I don't quite understand what you mean by social facilitation. Because to me, that is what pair programming does. It's different, but it sounded like
what may be confusing here is what Larry talked about is the terminology issue. Social facilitation is a term that arises out of social psychology, and the idea is simply that the expectation of evaluation by a knowledgeable other changes your behavior in some way, shape, or form. And so their studies are like, for instance, if you have little kids tying shoes, and you put someone in the room watching them tie shoes, they'll tie their shoes faster. But if you don't have someone, then if no one's in the room with them, stuff like that. So it's just the sheer effect of the evaluation pressure.
So it seems like that's sort of what I asked about earlier.
Yeah.
So the first and the third study are really just basically studying whether pair programming is studyable, right? Because it's whether you can replicate lab conditions and whether you can study people about changing them. And then the second one is something about pair programming.
Yeah. This one's a little bit weirder because we're really, again, trying to take it, yeah, in some sense this one assumes that you can do that in the lab, if you will. I mean, they're not really doing anything here that really resembles pair programming. We'd be doing small tasks, because the problem is if you have them actually write programs together, right, then the knowledge pooling kind of comes in, the problem negotiation effect kind of comes in, so you can't really isolate that slice in there. Any other questions? Okay, so I'm going to turn it back over to Larry. Oh, yeah.
This actually looks surprisingly to me like the same study of work that was done by Fred Brooks back in the 70s.
Mm-hmm.
And his conclusion was not this, that you do not take two people and place them on the same task. You take a rock star and you put a team around them.
Mm-hmm.
It might be an interdisciplinary team, and by doing that, you allow the rock star to essentially kick butt while the other people clean up. And his conclusion, I think, also during that process looked also at this same effect. And I'm wondering if you sort of studied some of that early work and concluded that there might be room for improvement in that early study.
I don't remember the Brooks study enough in detail to address that.
That's the mythical man month.
Yeah. No, I've heard. I just don't remember the details enough to specifically say.
His stated observation was that it's the surgical team where you have the chief surgeon, and then from the chief surgeon you have the cutters and the sutures and the anesthesiologist and the other people around that team. And so if you model that and transfer it into programming, you may end up with the same kind of division.
Mm-hmm. I will say, so one potential difference is that Brooks was really kind of trying to find the ideal team configuration, right? There are compelling reasons outside of that to use pairs, potentially. One is the distribution of knowledge on your team. If you have two people that write a piece of code instead of one person, if that one person gets hit by a bus, you still have another person. And conceivably that knowledge is spread out more to your team. That's a reason that's cited to us often by the people on these teams that are working in pairs. So if you're not looking at it from the perspective of what is the most optimal way to write software, right, but, well, optimal for a slightly different definition of optimal, right, then this phenomenon might be an interesting thing. And the other thing that we thought when we were going through this is, like, what can pair programming tell us about better supporting solo programmers, right? What can you get from looking at the way pairs work that can then come back and be like, what can we do in tools and other designs that better support solos from that? Yeah.
Similarly, there was a paper by Arvo or somebody or other on pair programming. Yeah. Promiscuous pairing? That's right, promiscuous pairing and the beginner's mind. And they found that actually having real beginners on a particular task caused more productivity than having like two experts on it, which was kind of counters the Brooks idea.
I would love to take a look at that study. You could get me the reference. Okay. Any other questions? I should really give it to Larry, so we'll take one more, and then if anyone has any questions, they can ask me afterwards. Are you sure? Okay. So, one.
It's always best to take questions if there are questions. We'd always rather have questions. You saw that data point up there, right? Got to ask questions. Okay. John tells me we can take a bit of time to ask what's next in terms of extreme collaboration. Not just extreme program, extreme collaboration. So a quick walkthrough, a quad chart essentially on where's the innovation opportunity. Most production work is over here, and that's the production code that runs and goes in the product. In my world, it's the engine valve that goes in the car. It's the manufacturing, finessing. It's designed by the numbers. We know the product, we know the process, get the damn thing out. The counterpoint to that is the innovation front end, the architecture front end. We don't know what the product's supposed to do. We're not sure how we should do what the few things we do understand. It's the foggy notion of what would happen next. That's where a lot of the breakthrough stuff is. It's when we go into new market zones that are often relevant, at least in particular to me. I want to point out two other zones that are often not really looked at. The product. We have the product. We know very well what the product should do, but we don't know how to get out to the market. What's the channel? What's the packaging? That's the entrepreneur. We have a process. We know how to make movies. We're very good at that. Send 10 million, send a decent script, you got a movie in 10 weeks. We don't know how to do the product. We don't know what the product is, okay? So this has turned out to be a strikingly important zone for innovation in ideal product development. Consumer products, but they make movies. Audi makes cars, they get their cars in movies, and it stretches them. Up here, it's the business sector that's driving you. There's a market, I got this. Now how do we get there? Okay. I hope you got the feeling for it. It's the feeling I want to get across because it's going after the next generation in design/architecture that I want to share with you very briefly. We have a new institute at Stanford. This particular slide doesn't give the proper name for it, so I'll speak it verbally. It's the Hasso Plotner Institute of Design at Stanford. How many people recognize that? The name? No? A few, fewer than I might have expected, because this gentleman comes from the world of software. And he has invested heavily in our community to bootstrap his organization to bring to software development the kind of innovation and user-centric values that have driven IDEO and our design program in product innovation. So I just share some images, but you'll quickly see that the images are just about people and brainstorming. Getting people to bend their brains together. This has become the icon. We wanted a school at Stanford. What was it going to be? I don't know. There's a Venn diagram at the top that tells you what it needs to be. There are people. This guy even gets a role in it. And we've got to raise millions and millions to make all this happen. How are we going to do it? So it's a lot. This is the icon for people working together. These are the crazy guys who make up the startup organization. A machinist. A rock star. He happens to have founded IDEO. A manager, an operations guy who makes sure the stuff gets delivered. A hardcore academic guy who studies people and how they think. A business school guy, it's all by the numbers, very, very analytic. An applied mathematician who likes people. A guy who doesn't like people, but he likes to study the organizations of people. That's not a fair statement, I take it back. Well, computer scientist who's driven to develop better tools for designers. The people who have to create the alternative futures of the world, he wants to give them better tools. I think that's pretty close to much of what you folks do. It's about people, and it's about the intersection of the disciplines. It's way beyond mechanical engineering, or electrical engineering, or software. In fact, engineers are just a little piece of the Venn diagram. It's all those other people that are part of successful organizations. Design thinking, what is it? It's almost always driven by working on projects, being embedded in projects, working in small teams who blend their minds, open their souls, trust each other, create things that can't be created in individual minds. I have no idea what they're trying to do there with that guy's mind. A familiar phrase, everybody in our business has to be a lifelong learner. Remember the noun phrase things? Every single project has to create learning. And the more we learn, the more quickly and efficiently we learn, the better our product outcomes. Notice this little line, you maybe can't read it. Each student is encouraged to develop their own personal process versus adapting to some standard process. And now that each person in this room has come up with a unique way of creating new products, new ideas, implementing them, now we come together in teams, and the team is richer because we have the diversity of styles, approaches, skill, and knowledge. Okay, slow down. So the Venn diagram we use, and I think I saw one earlier today, most of us come in this room from the technology sector. We build stuff. It's feasible to make what you want. Typically, we then go to the business community, try to build organizations that are companies that can deliver the goods, that make a profit, that are sustainable. Often, lastly, we come to the human services community, the human values community. Is this really good for people? Is it usable? Did we get surprise and delight when it happened? And the D.school is trying to bring design thinking to this diversity of participants. That's the extreme collaboration scenario. So when we give courses, there are students from all those areas brought together to focus on how to do the thinking that would deliver these outcomes. So in the courses running right now, students from these different departments and disciplines, we provide a physical place where they can come and work together. We provide management skills, organizational skills, logistics, and mostly we coach them to think about creating alternative futures. The creation side to counterbalance the analytic side of most formal education. Right now we're in a build cycle to put up new spaces that facilitate that kind of thinking. The average building, this maybe being one of them, doesn't facilitate that sort of open communication and interaction. We have one building on campus, the second one's going up, and that's the first technical barrier to effective innovation, the space you work in. We're replacing the product build lab, not replacing, we're augmenting the product build lab with a product experience lab. This happens to be a learning experience in this picture. It's very human-centered. The video recording of the world, the observation of the world, the building empathy for the user, getting into their shoes, living the life of a client, literally, are part of the methodology. And perhaps one of the most distinctive features is the notion of prototyping. I know lots of prototyping in the software industry, and it would take a long discussion to sort out just what it's about. But before you try to figure out what the perfect solution is, go build a crummy version of it. See what happens. Does it take you in the right direction? We have origins in the mechanical world. We build this stuff. Almost all the stuff we build today is computer-mediated build cycles. So there's a prototyping culture of testing your ideas and learning more from your mistakes than from your successes. Last year we did a prototype course in which the design teams were challenged to develop lighting for rural India where there's no electricity. And this is a team in the field. About 1,000 units were built. When the student team finished a 10-week exercise, they raised $5 million, started a company in India, built, tested, and matured the product there. So part of this notion of extremeness is to take on really tough problems, not just finesse last year's version, be a little smoother, but go out and change the world. So that's part of this overall notion that we can do more, we can do better, we can be more creative. We're mostly going to get there if we do it together, and we're only going to figure out how by trying. It's kind of a funny notion we should work together, but from pair programming to the business sector to working with clients in the world that can't afford our stuff, we think that's what's hot. And we hope there's a case for doing some projects with you guys in the future. We'll see what happens. That's it. Jan and I would be delighted to take questions, take suggestions, and actually have to do that at 45 per minute. I don't know if you caught this. I just saw it the first time. And in Jan's slide that showed the time to deal with an interrupt was about 1 minute 50. or 1 minute, something like that, almost came out to you could do 45 interrupts. So every question's an interrupt on your thought. Every time I challenge, but I raise something, then you have to turn your head and look another direction, and then you bounce it back, yeah, what if? And that's the kind of dialogue that is so fundamental and valuable to creative activity. Actually, it's creative activity that produces useful outcome. It's not just wild-haired creative. This is creative that makes the damn product work and work precisely and solve the problem that needed to be solved. Excellent, but I have to pass you a microphone. If you would, please. Speak to the tail end. That's not really a mic, that's just the antenna. But you have to speak to that end. No, not to that, to the button end of the device. Go, perfect.
So my question is actually about your open collaborative spaces. Since Microsoft is interested in that also, I'm curious what you mentioned hoteling offices, front yards, and back porches. In particular, I'm wondering what those mean. Those are open collaborative terms, and just what your thinking is on how flexible your space should be, et cetera.
Okay, it's about the space, it's about flexibility. The key word was hoteling. And here's a condensed version. The intent of the space is to be a place where students and faculty from across the university can come together, typically for units of engagement of 10 weeks. We're on a quarter system. So you assemble teams, you give them a place to live and work, hotel them. At the end of the period, they're gone. We record lots of that. We do audio and video recording, meeting notes, wall boards, brainstorm sessions, wikis, blogs, everything else, from the research perspective to better understand how it worked and what didn't work. Some projects will be longer. Each project will have maybe a different mix of disciplines, and we'll have to accumulate different kinds of knowledge. Some project may have to accumulate architectural fragments. So it's going to need a lot of space. Another project is just accumulating code. It just needs a big disk drive. So those will flex. So virtually no wall will be fixed. Most walls, when they're there, will be transparent. One of the killer issues is recording decent audio. So we have to have some acoustically isolated spaces. It's just possible that we'll end up that everybody wears a headset all the time when they're in a building. Partly to get a decent record, and partly because that's maybe the way we'll live pretty soon. One of the things we find as terrifically supportive of high-intensity teams that are co-located, and that's that they put their knowledge in the environment. They put slides, notes, Post-its, garbage, whatever it is. They put it up so they can see it and remember it, and oh yeah, that piece over there when you talked about it. All those things help us juggle more frameworks and more ideas per unit time, so that these spaces have to be able to store knowledge and be able to get rid of it again. So that's actually one of the really hard challenges. I happen to know IDEO's work. They have a large architectural design group. Being able to make work environments that allow rich temporary storage of stuff in the environment and then let go of it again. It's a technical challenge. Actually, it's a lifestyle challenge. Quickly illustrated with, most of you have offices with sound-absorbing walls. Take them all away. What do you get? Ooh, you get a lot more interaction, just eyeball to eyeball. I can see you now. You get a lot more noise, and all your stuff is exposed. And one of the solutions they came up with is, instead of us having offices where we store our stuff, we have walls on the side of the room where we store our stuff in common. So your books are next to my books, are next to Jan's books, and when you look for a book, you can see what everybody's got. And they use that in their own architectural space. It's one example that worked for them about collective access to each other's knowledge base, or experience base, we think is more important? Good question. You're getting into a new building, or some of you are. I heard reference to it this morning. So I jumped on that. Yeah, let's go redesign that building. Whatever they started, they probably didn't get radical. And here's part of why. I got to say it. The facilities engineering community looks at a building and sees a 50-year life cycle. Do they want you to mess with it every year? Change it around? Absolutely not. They want to put it up and treat all of us as ghosts that come and go. We don't have any role in the building and how it operates. And I went through this on my own campus. They won't let us make a flexible space because they're afraid actually we'll do something with it. And I think you're faced with that too. You know, the guy who's hired after you. Which, that was too many words for one question. More questions? Yes.
Did you think at all about the observational effect, separate from the collaboration one? And I'm thinking visually about this as the two guys are sitting working, and you've got a big 50-inch screen, and you can watch what they're working on from the open spaces with a cup of coffee. And is there a collaborative environment that builds around that supports the observational parts? Those people are not integrated into the process, but is that mere act of observation going to be an improvement over, or is that just
I hear a general concern. If you're observing, if you will, when is it ethical?
Yeah.
When is it socially responsible?
And when does it actually produce better results?
And should a work environment be manipulated to serve the observer versus serve the worker? And I would work backward. The environment's got to be for the people working there. If that big screen's helping them, that's good. If it's not, we're not going to. It shouldn't be there. And then observation is should only be by permission. And we're in an evolving world where we don't. It's getting slippery about when is an observation taking place. If something can record my email and observe it later, if somebody can record the air conditioning settings in the room and report later that this guy keeps changing the temperature. That's a project we have, believe it or not. If everybody in the room had their own temperature environment, there's some data out there that says we get a 10% productivity improvement. But then we'd start recording the temperature settings. The world in the social sciences and where the issue of observation is most frequently dealt with, they have rigorous approaches to keeping track of when and how you observe. Curiously, in engineering, we seem to be more open to being observed than social scientists are. So we had a major project where we instrumented a work scene that was mostly technical people, and they had no problems with the cameras on all the time. That's cool. I want to look at the record too. And then we brought in the anthropologist who might have benefited from that material. And they said, yeah, that's okay, but not the camera that could see me. And they literally taped over the cameras. We shut that down.
Follow up, then, do you think that's peculiar to a discipline like mechanical engineering, separate from, I'll call it the more private observation of the way programmers normally work, more mental discipline, as opposed to the physical, gestural effect that you see in mechanical engineering?
There are disciplinary biases, both in who tends to go into the fields, what their thinking styles are, work styles are. They are different. We have to finesse this each time for each group. Part of what we're exploring here is that more and more of these disciplines have to be professionally qualified. You're going to have to be able to work with others. And so that'll become part of professional development. It'll be part of what you get in school. You'll be led to understand that that's okay and that's valuable. You don't have to paint yourself a different color, but you might decide that, well, developing some of those skills, okay, yeah, I learned what? I learned the history of the United States. Maybe I should learn a bit of the history of southern China or something. That wasn't a good example. But as we increasingly work in cross-cultural teams, we're now extending the coaching model to being not just technical advice and process advice, but helping to understand cultural variables in the workforce. That's a whole nother subject. I think it will become more and more comfortable. And there could even be some really sizable change. For the time when we need to work alone, maybe we'll get an allocation from the company to have a first-rate office at home. But when we come to work, we'll know that, okay, I'm in the workplace now, there's going to be this shared interactive scenario. And just one little footnote, because it was triggered by some of the questions, that the social facilitation issue, I think that makes us uncomfortable. But, and if you look at high-performance athletic teams, nobody would dream of trying to put a peak performance team on the basketball court where everybody wasn't fired up and committed to winning that game and thumping each other and helping each other. And sure, there I'm watching to see if you screw up. I missed, throw the ball to me, not to the guy. We accept that there without problem. And I think it's conceivable we would accept it in a more intellectual zone as well. I'm sure we should cut at this point. So thank you all very much. Jan and I appreciate the opportunity to be with you. We had great conversations this morning where we were absorbing, and hope we gave something back.